Okay, everyone, so let's look at to the next problems. If you can refer to your textbooks, problem 7.21, page 341, we are given a case of a very long solid conductor with a radius of A, and we are also given the current that flowing through the conductor actually in positive z direction as shown here. So this is a 3D view, so we can assume that the length of the conductor is much larger than the radius, so we can assume it's very long, so that's why we can use ACL. So for the 2D view, from here you can see that this is from XY plane. If this is from top view, you can see that the current will look like a dot, right, because it's coming up from the plane along the positive z directions. Okay, we are going to find the H field that appear within and also the outside solid conductor. So since we assume that the L, the length of the conductor, is very long compared to the radius of the conductor, so we can assume this is infinite case. So then we have to use the ACL given as closed integral the h dot dl equal to the I enclosed. Alright, so again, if I want to find the H field for the first region, which is less than A, right? So again, we need to draw our Ampere loop anywhere within the conductor. Let's say this is my point of interest. So if you want to draw the loop, it must obey two conditions. The first one, it must pass through the point of interest, and also it must be completely closed. So let's draw together. So this is your Ampere loop, which having a radius of r, which is any value, right? Which must be a variable, any value of radius. So that's our sensor or probe. So from this equation, we know that we can find the current through the volume current density. So we know that the total current flowing throughout the surface here actually is I. So we can simply find the volume current by dividing the total current over the total area, right? So from here you can have the I given in equations, and now just divide by its area. So this is since a circular area, so you can just put pi a squared, and we know that the J here, guys, flowing in positive z direction, so you can simply put the z direction and H unit of ampere per meter squared for sure for the area. So that's our J. So based on previous lecture, we can simply find the I enclosed within any Ampere loop by integrating the J dot ds. So again, now let's proceed. For this left hand side, for the sensor part or for the Ampere loop, again, since we are drawing the line in circular shape, so we can simply have these conversions 2 pi r representing our circumference path is equal to integrations again J dot ds. That's how we find current enclosed within a loop for the case of volume current density. So since the J here, guys, in z direction, so for sure, or by right, the ds also must be in z directions to make it valid. Otherwise we're going to have zero value. So again, so from here we just take a sample. So let's say this is my sample ds, right? The ds. Alright, so get this s here, guys, can be expressed in this form since a vector again z component. So now we have here r dr dphi, because this sample only depends on these two parameters, which is r and phi, whereby the z remain constants. So let's put the substitutions over here. Gonna have h 2 pi r over integrations the I in z directions over pi a squared, this one for the J, the current density, and then a dot with the ds as shown up here. So again, Z R dr dphi. So we know that the z dot z will have 1, so take out all the constant outside of the integration part. So now we have I pi a squared integrations r dr integrations dphi. Alright, so how do we determine the limit of the r? Look at carefully from this diagram. We draw the loop actually from 0 to the r, so it means that this is only the area, or this is only the current that we are looking for. So we just integrate the r, which the limit starting from 0 to the r. Alright, so we don't care about the area outside the r, so now just put 0 to r, and also the phi same for 0 to 2 pi. So let's proceed this integration. We're gonna have here I r squared over pi a squared. Now we have it 2 pi. So you can simply delete, right, this 2 and 2, the pi and pi. You're going to have this one I r squared over a squared. Okay, so let's take out this 2 pi r and put down there just one h only. So the h, I have here I r squared 2 pi a r. So again we have r, you can just simply delete the r, only one left. So now we have here finally the I r 2 pi a squared. So now since we know that the h in phi direction, so we can simply put a bar there and add here in phi directions, and we have unit of ampere per meter. So that's the h, guys. Let's say the h1 I define here, the h that exists within the conductor. Right? So how do I find the h that appear outside the conductor? So the same approach that we used last time for the case of second regions, which is the r is more than a. Again, we have to draw our Amperian loop that pass through the point outside the solid conductor, and also must be completely closed. So that's, let's say this is your Amperian loop for the second regions. Let's say this loop has a radius of r. Again, must be a variable because now it presenting your sensor or your probe r. So now again applying the same law, integrations h dot dl equal to the I enclosed. Now again, if you look at carefully from this diagram, if you can see that within this Ampere loop, it covers the whole total current, right? The current that flowing from 0 to a, which is I. It covers everything under or within this loop. So you can simply put the I enclosed become the I total, which is I. Done. Alright. So again, this part gonna have h 2 pi r over I, and lastly gonna have the h equal to the I 2 pi r. So since the h, we know that in phi direction, so you can simply put the phi component and a bar there, and has a unit of ampere per meter. So let's define here become your second h. Right? So this is your first h within the conductor, and this is your second h outside the conductor. Alright, guys. Okay, so let's look at the next part of it. I want to show you the next operations of del operator. If you can recall, last time we have covered 3 del operators so far. The first one, we have a case of gradient, grad in any equation, let's say A. So this is a gradient operations. And also we have the other one here, divergence, del dot any vector. So that's called a divergence. So this case, let's say we have this example, gradients divergence of D equal to the rho V. So that's our first Maxwell equations. And also for the third case, we have here Laplacian of any equations. Now we have example as well using Laplace equation or portion equation. Let's say here del squared V equal to a negative rho V over epsilon. And lastly, I want to show you the fourth operation that del has here actually deal with a cross operator, which is del cross any vector. So now we have here the name of curl of A. So if you want to pronounce it, just curl of A. Alright. So now we have to, I want to show you how do we model the H field with using this fourth operation of del. So now in this case our H, now our case the vector now is H. So we have two H, right, already. The first one H1 given as IR over 2 pi A squared in phi directions, and then for the H2 we have previously given as the I over 2 pi R in phi direction. So these are the two H that we obtained earlier for the case of solid conductor. Right now we want to prove, so we want to apply these curl operations or curl of these two vectors. So for this case, let's look at your table in your textbook. I think the page 85, and look at to the table 3.45 under category of cyclical structure. So based on the table you can see here, curl of H is equal to the 1 over R d H z over d phi minus d H phi component over dz. So this whole term belongs to the R directions, and then plus again d H R component over dz minus d H in z component over dr, and also this whole term belongs to the phi directions. Well, let's proceed to the third one, plus now we have 1 over R, we have here d over dr, and now we have R H phi minus d H R over d phi. So now whole term belongs to these z directions. Alright, look at carefully. Let's want to perform the first one, curl of H number 1. Alright, so that's our first task now. So this is our H1 field. If you see closely from the equation of H1, we know that the H1 only exists in phi component. So by that, this is the value of H phi component. Alright, so we don't have any H in other component. We don't have also any H in Z component. So by that, we can simply ignore this term because we don't have any HZ. We also doesn't have any HR. Also this one also will have 0 because we don't have any Z component. Same thing goes to down here. We also don't have any in R component, isn't it? So now look at carefully to these two left components up here and down there. So this one, even though we have H phi, but we are going to differentiate over dz. However, in this H phi equation we don't have any z variable, so but if you differentiate this the whole term over the z, we also will have a 0, isn't it? Because the h component here doesn't have any z variable. So after we differentiate over the z, we'll have a 0. So now just let's focus only this left term down there. So it's equal to the 1 over r d over dr r, and let's put the h phi here from this one, the h phi number 1, so the I r over 2 pi a squared, and now have the z directions. So let's proceed performing the differentiation process. Now we have here I over r. Now we have here I r squared over 2 pi a squared. Don't forget the z is equal to 1 over r. Now after you differentiate, you'll have here 2i r over 2 pi a squared, again in z directions. So now let's simplify the equation with the r here, delete with r there, and so the 2 there will delete each other. So now we can simply put this equation, curl of h is equal to the I z component over pi a squared. Alright guys, if you see closely from this equation, actually this equation represents our volume current density, isn't it? So we can simply change to become J, right? So that's from here, you see the J is equal to the Iz pi a squared. So that's actually our J, right? So we can simply change this whole term becoming a J. So finally you can have these simplified versions of curl of H, which is equal to J. And guys, this is our third Maxwell equations in point form. Okay, so let me note down there. This is our third Maxwell equations in point form. Right? Alright, so how do we perform for the second H2 is shown here. So what should be the output? Is it same or not? So let's try together. So the second operations of curl of H number 2, again using the same term left here, the rest equal to 0. So 1 over r, so d over dr. Now r. Alright guys, look at carefully. For this H2, this whole term becomes your H phi component, right? So just replace this H phi with this H phi component from the H2 field. So now I'm put here the I over 2 pi r. Alright, look at carefully. Before we do differentiation, we can just simply delete this r and this r. So now only left constant. So differentiate over constant, we're gonna have a 0, right? Because after we delete this r, so we only left the I over 2 pi, which is only constant. So differentiate over constant will have 0. So now we have 0. My question is, what does it mean? If you see closely from this diagram, if you perform the curl of H for the H1, which is inside the conductor, so we are going to find the J, because the J only exists within the conductor. So if you perform the curl of H number 2, which is outside here, so we have 0. Why? Because we don't have any current outside the conductor. So that's why for these operations we are going to have 0, which shows us that there's no current outside the conductor. Okay guys, so that's the idea. So I hope you can try yourself and make sure you redo. If you have any question, you can just ask me at any time. Okay, so thank you and all the best.